as I said from last video, in this course, we're mostly concerned about the product measure of two measure space. So suppose I have two measure space, xa mu and yb nu. The goal of this video is to define a product measure on their product sigma algebra, which is, I write this A tensor B here. So just a bit of intuition. So the product measure on this new measurable space of their product measure, well, you kind of want to, you don't want to define an arbitrary one, okay? So suppose you are given some of these boxes, okay? So here A comes from X and B comes from Y. Then the idea is the measure of this box, okay? Just by intuition, what happens on the real line when you have a box, you want to give the measure of this box or the area of this box to be the product of their length, okay? So you really want this measure to be mu of A multiplied by the nu of B, okay? Or the area of a box. So you really want your product measure to satisfy these this property. So if I call the product measure to be the product of mu times nu, okay, so you want this box to be equals to that, okay? So that's kind of the goal or the ideal of the ideal property of this product measure, okay? So how do we do that? Well, there's one way to kind of extend these formula, okay? So we have this nice theorem about Carathéodory, okay? We have the Carathéodory extension. If I can define such a measure on an algebra and that satisfies this desired property, then this property will be preserved if I define it on the algebra. By the Carathéodory theorem, the extension will satisfy this property as well, okay? So that's what we're going to do, okay? So we first of all need to define an algebra. Well, if you just take these boxes, they are never going to be an algebra because the union of two boxes is not a box anymore. Usually it's not a box. Okay, so first of all, we need to define algebra. Well, it's similar to what you see when you define the Lebesgue-Stieltjes measure. You do these half-open intervals. Their union is not one, but you just take a finite disjoint union of them. Okay, so we do the same thing. Okay, so here let's just use some notation. Let's call it C because we already have A and B here. Let's C to be all the finite disjoint union of these boxes. Okay, union of let's give them name. So AI times BI, where of course, I need to require the AIs to be in the corresponding sigma algebra A, and BI is in the curly B, okay? So this is a set of collections of sets inside the A cross B. So this is clearly contained in the product sigma algebra because we saw last time the boxes are inside the sigma algebra. They actually generate this A cross B. And I'm only taking finite disjoint unions, so of course they're inside here, okay? So why is a C an algebra? So this is fairly easy, so let's make the following claim. I claim that the C is an algebra. Why is it an algebra? Well, first of all, if I take the intersection of just two of them, so let's say A1 cross B1, and I want to intersect A2 cross B2, well, if you draw a picture, so you have one box and you have another, so their intersection looks like a box. So you just convince yourself this is the union, the intersection of their corresponding coordinates, and you time them together. Okay, so you have this inequality. So the intersection of two of them is again a box. So finite disjoint union of these boxes. When you take the intersection, you just intersect the corresponding AI times BI, and you will have their intersection is again a box or a disjoint union of box. And you also need to check their complement. Okay, so if I have A1 cross B1 and I take the complement, well, what the complement looks like is that, okay, so you have A and you have a complement and you have B and B complement. Okay, so here is your A cross B. So its complement looks like the union of 3 disjoint boxes. Okay, so you can write it as let's say A complement cross B. So maybe I should remove the subscript. Okay, so let's just do A cross B complement. Okay, so it's A cross B and you union the A cross B complement, and you union the A complement cross B complement. Okay, so you know C is closed under intersection, closed under complement, and you can verify, of course, is closed under finite union. Okay, so C is an algebra. So exercise. These two is enough to tell you C is an algebra. Okay. Well, so now we know it's an algebra, so they are a collection of disjoint union of these finite disjoint union of these AI, BI, and we know what measure we want to assign for these AI times BI. Okay, basically their product. Okay, so now let's define a function. So let's give it a name. Let's call it tau probably. So let's call tau of A cross B. Let's assign it a value of mu A times mu B. That's the desired value I want. Okay. So I want to define tau on this algebra C. So tau of the union AI cross BI. So here the union is a disjoint union. So it's a finite disjoint union. Okay. So I can just assign it to be the summation of over I. So here I going from 1 to n probably. I going 1 to n. And you do the mu of AI times mu of BI. Okay. So you now define a function tau on from C to the positive reals. So if you want to extend it to a measure, okay, this tau is satisfied this nice property you like. So you want to extend it to a measure and invoke the Carey-Theodori. So we just need to show tau is a pre-measure. Okay. So here's my the main proposition of this video. We want to show tau is a pre-measure on this product sigma algebra A cross B. Okay. So tau clearly is maps empty set to 0. So to show it's a pre-measure, we basically need to show the following. So we want to show that if A cross B is equals to a countable collection, so let's say I greater than or equal to 1, it's a countable union of some AI cross BI, then we need to show, to show that tau of their product is equals to this countable summation of tau of AI cross BI. Okay, that's essentially what we need to show. Once we show that, the rest follows fairly easily because everything inside C is a finite union of these boxes. Okay, so you can show it fairly easily. Okay, so to show this, well, essentially, let's write by definition of tau. So this tau is, by definition, this is mu of A times mu of B. Okay, so I want to show that this is what I want. Okay, I want to show that this is equals to the summation of mu of AI with mu of BI. Okay, so this is the goal. Well, to show that, we first observe the following. So for every x and y inside the x, well, let's say x and y, the pair inside the product space, if I consider a function, let's consider chi a of x, well, that's well defined because chi a is the characteristic function of this A. And then I multiply a chi b of y, okay? Well, you can see that this one is give you a 1 if both of the characteristic function is 1. So in other words, if x is in A and y is in B, and it will give you 0 otherwise. So basically, it's the characteristic function of the A times B, okay? So immediately you know that these chi A function, this chi A of x, chi b of y, is going to be equal to the summation I greater than or equal to 1 of chi of AI x, chi of BI y, okay? So here you're really just treating x and y are just elements of x and y respectively. This is not a function on x cross y. Okay, so chi a is just defined as a characteristic function on x. Chi b is a characteristic function on y. We're not integrating anything on the x times y yet. Everything is understood in the x and y, their measure space. Okay, so now if I fix an x, or let's maybe fix an y, okay, just fix a y inside y. So you can pretend everything related to y, that's just a constant, okay, that's a constant if you fix on y, okay, so because they are constant, okay, so now you just treat this star, let's call it star, you treat this as a equation of a function on x, okay? So the left-hand side is some constant, you just pretend chi b of y is a constant, times this function, this characteristic function. On the right-hand side is equals to the summation of a bunch of these constant times the characteristic function on ai. So by the MCT, because everything here is non-negative, you can just do the integral, okay? So you have chi b of y times the integral of chi a of x. Here you do the integral with respect to mu, so let's say mu of x. So you're treating it as a function of x. Okay, so this is the equals to the integral of the right-hand side. Okay, so you can pull out the scalar. So this is chi of bi of y. That's the constant, you pull it out. You do the integration of the function on x. Okay, so this is d mu of x. MCT allows you to say they are basically the same. And the integral, by definition of integral of a characteristic function or integral of the, you can treat it as a simple function. Okay, so this is just mu of a. Okay, so you have mu of a times chi b of y. Now is equals to the summation I greater than equal to 1 of each one of these is mu of ai times this constant chi bi of y, okay? So now you kind of reverse it. Now you treat this mu of a and mu of ai, they are constant now. They are not functions of y. Well, they're really constant actually. So you already integrated the x out. Okay, so you by the MCT on y again, okay, you're having a linear, well, on the right-hand side is some non-negative function, and then the left-hand side is also non-negative, so apply MCT. So you integrate, so you pull out the scalar, you just integrate the chi b of y, now respect to the measure on y, so mu of y. So this is going to be the summation of, you pull out the scalar mu of ai, the integral of chi of bi of y, okay, and the mu of y. Okay, so this tells you basically what you want. Okay, so mu of a, mu of b is equal to this summation of mu of ai times mu of bi. Okay, and this is enough to show that the tau you define is a pre-measure. Okay, so I'm not going to write all the details, so you can convince yourself this is enough. Okay, so now what we get is that tau is a pre-measure. So now once we have a pre-measure on an algebra, on the algebra C, so automatically you can apply the Carathéodory theorem and you will get actually a complete measure. Okay, and you know the complete measure will contain the sigma algebra generated by C, and it's fairly clear the sigma algebra generated by C is the A cross B. Okay, so by dropping it down to the sigma algebra generated by C, you get actually a measure on this product sigma algebra. Okay, so let's call it a theorem. It's really just a corollary based on the tau is a pre-measure. Okay, so theorem. So let's do the setup. Okay, so let's let x, a, and mu, and you have y, b, and nu. Okay, nu to be measure space. Okay, so then what you get is that there exists a measure. Okay, let's say there exists a measure. Let's call it tau bar for now. Okay, so tau bar on the product space x times y and a tensor B. Okay, you only care about it on the product sigma algebra. And this measure tau bar will satisfy the desired property you want. So you have tau bar of A cross B. That's just equals to mu of A, nu of B. Okay, so here for every A inside the sigma algebra A, B inside the sigma algebra B. Okay, so this tau bar is just really the Carat-Theodore extension of the pre-measured tau restricted on the sigma algebra generated by the algebra C, which is equals to A cross B. Okay, so there's nothing really to prove here. Okay, we already proved all the hard part. We already proved tau is a pre-measure, so do the Carat-Theodore and the theorem should follow. Okay, so just now we can denote this. Usually we don't want to write a tau bar, we just write this as a mu cross nu. Okay, this is called so it's called the product measure. Okay, so by saying the product measure of two things, so I have two measures, mu and nu, then the product measure is this tau bar, this Carat-Theodore extension that satisfies this identity here. Okay, so we call it the product measure.